Carver Mead, he made his name in the semiconductor industry and as a Caltech professor of electrical engineering, but his real innovation is a material understanding of electrodynamics.
Yeah, and he sees light as this bidirectional transaction between atoms, which is a somewhat forgotten idea that was initially proposed by Lewis, who was a very famous chemist who gave us the covalent bond, amongst other things. And he's resurrected this with full mathematical rigor, and it's led to some really fascinating interpretations of the latest Nobel Prize experiment, which is actually like a 60-year-old, 50-year-old experiment. Um, just an amazing conversation. This is obviously something we toy with on the show all the time, is trying to make sense of light and electromagnetism in terms of what the atoms themselves are doing. And this conversation brings us one step closer to making more definite statements to that effect.
And so if you like what we do, support us on Patreon. We are at patreon.com/demystifysci. You get to come to weekly Patreon meetings where you get to give direct feedback to the things that we're doing at the show. You can help steer the ship. If you've already done that, go ahead and just share the show with someone. And if you already support us, thank you. Thank you. We couldn't do it without you. Enjoy the conversation with Dr. Carver Mead, and we will see you next week.
The scientific revolution starts now.
The Demystify Sci podcast.
Let us see the dark.
Today we're going to talk about physics, which is we're going to talk about the Nobel Prize, we're going to talk about the implications that it might have for the future of the discipline, things that have been going kind of wonky over the course of the last, 50, 60 years in physics. But you didn't begin as a pure physicist. You started out in the semiconductor industry. And so what was your path like to get to the place where you were actually thinking about these physics questions?
Well, actually, it happened in a very natural way. I was in electrical engineering, and the transistor was just becoming a thing. So we had this brand new faculty member by the name of Dave Middlebrook, who showed up on our faculty at Caltech, and he had just written a book on an introduction to junction transistors. And it had a very brief description of the physics inside the transistor. And so I got interested in what was it in the physics that made the device work and limited how fast it would switch and that sort of thing. So I did a thesis on what the physics of the transistor made it so poor a logic device, because the devices in those days were junction transistors, and they worked with minority carriers. They used diffusion as a mechanism for moving the carriers from one side of the transistor to the other, which is a very slow process. And they stored a lot of minority carriers inside, so when you try to turn them off, you had to get all those minority carriers out of there. And that was so I did a thesis on how the physics of the transistor limited what you could do with it.
So I have a question. Is it common in that industry at the time for folks to try to understand the physics or before working on these designs, or are people doing some version of trial and error to maximize the efficacy, or what's the word? Efficiency, I guess.
Well, it was mostly the latter. And the people who were doing the physics and making models of the transistor, there were Ebers and Moll had written this horrible set of papers that just went on and on and on with these god-awful nonlinear equations and you couldn't really understand from their models. And in those days, you didn't have computers that you could program them. And their models didn't really and they didn't really represent the physics that was limiting. So, and I realized that, the physicists were doing these wild, theory of their own, and the electrical engineers were just doing what you said, and just, trial and error. And I wanted to understand how the things work. So it isn't hard. You get a bunch of them and you measure them and try to figure out what they're telling you. And, the physics inside is pretty simple, and you work on it until you understand what they're doing.
Could you walk us through the physics of the transistor at the time?
Well, it's like any experiment that you have to make measurements on it and put certain kinds of signals on it and look at how it responds and run the temperature up and down and do a bunch of things to figure out what's going on inside.
I mean, not necessarily the experimental process, but the theoretical, like, how does a transistor work for the audience who's watching who might not know?
How has that changed? How has that understanding changed?
Not very much. The understanding of the first order understanding of the transistor had been worked out by Shockley and Bardeen and those people, and it's pretty simple. But then when you get a real device and want to use it in a real circuit, like a logic circuit, now you want to know, how do you characterize the device and how is that related to the and of course I could cut the devices apart and see how big they were and stuff, so I could, that's just plain old hacksaw. And yeah, it was just a so that's how I got into the physics, trying to understand what was making the transistor so bad. And
did you have some basic physics realizations that helped you come to terms with that? Can you explain that to us?
Well, it was interesting that I wrote up my findings and nobody had done it. They had small signal equivalent circuits for the transistors, but then nobody had worked it out. So you could, do switching circuits with them. And it's kind of funny that nobody had done it, but so I just did it and did a thesis that way. And then, so I was into the right at the border between the physics of what was inside and the way you use it in the circuit. And that's sort of where I've been my entire career, is on the border between the electrical engineering side and the physics side. And you really have to be able to go back and forth across that border if you want to really do anything. So.
And this is like the difference between talking about what atoms are doing versus talking about electrical potentials at different, icons, essentially, at different steps in the circuit or something like that.
Yeah, all the current densities and all the stuff electrical engineers do. And it's odd, but most theoretical physicists aren't comfortable with electrical engineering notions, and so they don't do that part.
What do you mean by that?
Well, I remember talking when the quantum Hall effect came out. I remember talking to a fellow who was one of the authors of a book on the subject, and I was talking to him about my thoughts on the subject and how the current was flowing, and he said, "Oh, we don't have current in our devices." I said, well, the whole point of the device is the relationship between the current and the voltage, and if you don't have current in the device, it's useless.
What did he imagine was going on?
Yeah, well, you have to write down a Hamiltonian, and you do all this, standard stuff, and you can get certain answers that way. And so they got these states of the electrons, not the states, but the properties, excitation properties, that sort of thing.
And what is
So
the Hall effect?
The quantum Hall effect
Yeah.
has become the, if you take something like an MOS transistor and put it in a big magnetic field, you find that as you change the number of electrons that are in transit between one side of the transistor and the other, that the current has steps in it, and those steps are related by the H bar and the charge on the electron, and so that has become our standard of resistance. The international standard of resistance is now the quantum Hall effect, because there are these quantized steps. And the easiest way to think about it, which is the way I think about it, is charge is quantized and flux is quantized, magnetic flux is quantized. So if you quantize both of them, then the ratio gets quantized, and that gives the resistance. So it's a very lovely. So now we have the Josephson device gives us the standard for voltage, and the quantum Hall device gives us a standard for resistance. So
can I ask you a really basic question about that?
Sure.
So, like, remind me, flux has to do with the rate of change of the charge at some given location.
Well, if you the magnetic flux is the amount of, if you think in terms of magnetic field, it's the amount of magnetic field in a certain unit area.
It's like, I see.
But it's also the integral of the vector potential around the periphery. And the vector potential is volt seconds per meter. So you integrate that around and you get volt seconds. And
so my question is, what do you think that charge tells us about what the atom is doing? Have you thought any about that? Like, what the atom is physically doing during this event we call charge?
There's several levels which you could think about that question. Nobody understands what charge really is. We know a lot about it. We know that if you move charges, you get a current, and if you stack them up, you can get on a capacitor, you can get voltage, and we electrical engineers use them all the time to do everything. But if you just drill down all the way and say, what is charge? It's a quantity that gives us all these wonderful behaviors, and some of our elementary elements of matter, the electron and the proton, have it, and the neutron doesn't have it, or reasons that they wave their hands furiously and use group theory and all that. But nobody really understands what it is. We know a lot about it.
It strikes me that if the electron is sort of the outer surface of the atom, that the concept of charge has to do with the motion of that surface in some complicated fashion that perhaps we haven't come to understand yet.
Well, certainly current is the motion of the charge. And that we understand very well. And the charge is, we know what charge does electrically. You can put it on a capacitor and it gives a voltage, and if you move it, it makes a current, and you can make electrical circuits and do all kinds of very fancy stuff, which is what I've spent my life doing. But then when you go really deep, it's just something that we know does all these things. But exactly what it is a deep question, very deep question.
I want to get back to I want to come back to the question of what exactly is charge, because I think that it's interesting, and I think that having a physical interpretation of it does help understand what exactly is happening. But you said something that was really interesting, which is that we have a good understanding of current. And we actually did a brief investigation about this recently, and it seems like there isn't really quite a consensus of what is current, because it moves faster than the flow of electrons does through a circuit.
Yeah. You have to be very careful. There's a lot of discussion by people that have only a surface exposure to these things. And it's easy to get confused. And so there's a lot of confusion on the web. And you can't let it distract you too much, because there will always be confusion. Once you admit that there's this thing called charge, and if you stack up charges, you get a voltage, and the voltage is a potential. Physicists don't understand the notion of potential very well. They think it's a mathematical thing. But actually, it's the thing that makes all electrical things work. It's the number one concept that every electrical engineer embodies in their being before they can be an electrical engineer. And so the fact that potentials aren't the working medium for physicists, and they are the working medium for electrical engineers, has made a bifurcation between the two fields that, of course, I've been on both sides of that. So it's hard for me to realize that there's this group of very smart people that just aren't comfortable with the concept, and so they don't work with it.
Yeah, that division is really fascinating. The division, just the division between science and engineering is very fascinating, and how the engineering has, in some sense, swallowed up some of the science, and then the science is, starting to adopt different engineering techniques, and it's almost like people have forgotten what the difference between the two is, which is strange because there's institutes of science and technology, but most people think of them as the same thing.
Well, if you look at what really happens, the real discoveries are made in the lab, like the quantum Hall effect and the Josephson junctions, and all of those things are made in the lab. And the theory follows. The theory always gets made up so that it, quote, predicts what's been discovered experimentally. So you have to be very careful. I have a list of I want to get, I want to send you people a copy of my little green book. So if you send me your mailing address, I'll get my admin to send you a copy of that because it has in it a list of the really great discoveries that have been made in the last, since the World War II, roughly.
Mm.
And
Fantastic. We're trying to assemble a bookcase of all of the people that have been on the show that have written books. So we'll definitely put it in a position of honor if we got it.
yeah.
But before we move on from the question
Well,
I had,
let me just finish the thought
of course.
because it's very important. I have a list there of all the really fundamental breakthrough things, and they've all been experiments. And most of them were denied by the theorists until they were observed. And then, quick like a bunny, the theory got changed enough to where it would predict the thing that had just been observed. So
there's something really interesting in physics, which is very different, I think, from biology or chemistry. Maybe chemistry is similar, but in physics, you have this idea that a theory is like a mathematical formalism of some phenomenon. And in other sciences, I want to say like chemistry and biology, it's more of thought of as a mechanism for how some physical material objects interact to produce a phenomenon. And that's a really interesting divide because the mathematical formalism is really useful for engineering at some level, right? Of course, the abstractions get carried away sometimes, and it's, maybe better to just use Newton's gravitation laws instead of Einstein's in some cases or something. But generally, it seems like physics is well suited to engineering, whereas
it has been in the past. At the present time, the way physics is taught, quantum mechanics is taught as a purely mathematical algorithm. And what it is it's laid down as if there's only one kind of question you can ask and there's only one kind of answer you can get. And you have to do a measurement, what they call a measurement, to get the system in an eigenstate. And then that's a result that they can calculate. Now, it turns out that what they're forcing all the students to do is to become proficient in this essentially as little robot calculator people.
Oh, no.
And the answers you get actually are probabilities, only probabilities. And they're probabilities of the state, the final state, being in some mixture of the eigenstates. Well, you don't know the eigenstates. So for it to have any physical meaning, you have to now go and calculate all the eigenstates. Well, for any real situation, that's a really hard problem because the entire theory is formulated with a new three-dimensional space for each electron, or each degree of freedom, as they would say. They have a whole space for a mode of the electromagnetic field. That's one three-dimensional space. And they have a three-dimensional space for each electron. So if you have more than a few things...
Probably have a few electrons in a circuit.
Yeah. Well, they of course become extraordinarily clever at working with this mess. The reason for the mess is that if you have more than two electrons, let's just talk about electrons. The same kind of thinking works for protons too, but let's not get into that because there's been very little progress made in understanding nuclei since World War II. So there's a bunch of observations, good experiments, but in terms of understanding, it's still surface. They have what they call a liquid drop model that's existed since World War II, and so it's so. Let's just talk about electrons, because when you read stuff, that's mostly what's going on.
So you're saying we need another world war to hammer out what's going on with the nucleus?
No, what we need is young people that don't get tangled up in what happens in physics now is they get told, okay, you get good at doing this algorithm, and we'll give you all kinds of problems you can do with it. But if you're making experiments, those calculations are mostly useless, the ones you can actually do. So then what happens is that the quantum chemists go off. It turns out you can do the first principles calculation for up through about the middle of the first row of the periodic table. You go lithium, beryllium, boron, maybe carbon, and then it gets too big a space because you're getting a new three-dimensional space for each new...
Like each new orbital surface, like they start getting these really crazy contortions, the surface of the atom.
Yeah. So it turns out that the religion of doing this little algorithm has become such that anybody who asks questions about, like, well, what's really going on in there, buddy, you don't belong in physics. Just shut up and calculate. So they've basically driven all the understanding out of physics. Now they just grind on. They get a Hamiltonian and they grind away and do their thing, and then they publish papers about it. And so it's not helpful for almost any engineering thing. It turns out all of us who've done, quantum things on the engineering side have had to go back to the beginning of when Schrodinger wrote his first one electron thing. A lot of problems you can factor into single electron things, like one orbital in an atom, and then you can couple that to a electromagnetic field, and you can calculate that problem simply. You don't have to go into multidimensional space, and you don't have to do hocus pocus. So we've all gone off and found our own way to have our quantum mechanics that works for us. So actually what has really happened is the quantum stuff that you read about that actually works has been worked out by the applied physics people and the electrical engineers that do fiber optics and nonlinear optics and various electron devices like we've mentioned.
And so what would you bin as quantum stuff that works versus quantum stuff that doesn't?
Well, the quantum stuff that works are things like lasers. Lasers, Charlie Towns, when he first came up with the idea for the stimulated emission devices, it's in his descriptions in his oral history. He went to Bohr and Heisenberg and von Neumann and talked to them about it. And they all said, buddy, in effect, they said, buddy, you just don't understand how quantum mechanics works. It's about probability. Well, a laser is not about probability. A laser is about a coherent quantum state. Superconductivity is about a coherent quantum state. That you can build all of electromagnetism from a coherent quantum state. That's what I did in my little green book. physicists missed all that. So the fact that they fastened on their statistical physics that can't get any other kind of answers has really made a mess of physics as a field. And so the progress has been in applied physics and the electrical side. And so there's been huge progress there. And it just went away and don't worry about the physicists because they're not going to get it.
Yeah, I love how you are looking at this in terms of. I love how the coherence idea comes to play in how you look at the system as a whole, and by simplifying the quantum behavior, by looking at it as this network behavior, you can start to think about how these atoms are actually interacting, as opposed to each doing its own thing in isolation.
Yeah. It's in most of the problems that actually come up, like you follow the latest Nobel Prize in physics.
Yeah, I want to hear your thoughts on that.
Yeah. Well, I sent you a reference to my archive paper with John Kramer, and the last section in that paper was an analysis of Clauser's original experiment that showed entanglement. And it turns out a simple photon, which takes all the energy in one atom and transfers it to, another atom. Photon is.
That's pretty revolutionary, by the way. I must say, like that. You pointed out when we talked earlier a reference to G.N. Lewis, yeah. But it was sort of lost. Like if you look at the basic textbooks right now, a photon's thought of as just this thing that shot off into the dark. But to think about it as an interaction between atoms, I always thought of it this way. I'm surprised to find later on that people don't think of it that way. But it is rather revolutionary.
Yeah, and it isn't that Lewis didn't have a clear notion of it. He did have a clear notion of it. Wasn't worked all the way through. Still hasn't been worked all the way through. I did a next step in the paper with Kramer, and it's clearer there. It isn't finished in the sense that we've always had a sense that if energy goes from one atom to another, it has to pass through the space in between. And in traditional electromagnetic theory, that's called the pointing vector, and it carries energy in the field. Well, it can't be right, because if there was energy in the field, there'd be 0-point energy in the field, and the cosmological constant would be it's now down to only 10 to the 60th out of bounds. It used to be, it started out about 10 to the 120th. Too much energy if you had 0-point energy in the electromagnetic field. So it isn't. So,
and 0 point is, can you just clarify that real quick? So 0 point means that there's some place where there is no energy in the system, essentially?
No, it comes from the notion of a quantum resonator. If you take an electrode and put it in a potential well, the usual first problem you do, it makes energy levels. And the lowest energy level, of course, the electron has a wave function that has, a shape, and it's confined. So if you confine the wave function, that means it has it's a little standing wave, and that means it has a momentum. Momentum being just the derivative of the wave vector, if you like. it's a standing wave, so it has two wave vectors that are equal and opposite, so it keeps it together. So,
and by the way, from the standpoint of the atom itself, this is the same wave function that we would transform to derive the shape of the orbital itself.
That is the shape of the orbital. Yeah, and it's confined by the potential of the proton. So then its energy, its lowest energy, isn't zero because it's confined, and so it has. When you do the Schrödinger equation, it's the second derivative of that, which is a finite thing, so that the fact that it has that second derivative gives it an energy.
And like, to me, this says that the shell of the atom is in some frenetic state, and then when it goes to a new energy level, it's in a more frenetic state or less frenetic state. And it's almost like saying, well, the atom can't stop moving, like the shell can't stop moving, something like that.
Yeah. Moving is a
requires a reference frame or something. I understand. Yeah.
No, it's not about that. What it's about is that the wave function has a frequency, but it's a standing wave, and so the standing wave, the amplitude is changing with time, but the charge density isn't moving. So it's a standing wave. It just has a stationary charge density, but it does have a frequency. What does that really mean? Deep question. You see, you don't have to get very far before, and people will say, oh, but if you use a Dirac equation, you get negative frequencies and positive frequencies, and one's the particle and the other one's the antiparticle. That's maybe a good way of thinking about it. In which case, just the existence of the thing has a bunch of energy. Well, it does. It's called the rest energy of the thing. So that instantly gets you much deeper than you need for any of the simple things about atoms.
But how does this relate to the question of 0 point energy in between the two atoms that are exchanging the photon?
The thing that got people balled up to the point where it's still balled up. If you look at Peebles just wrote a very nice review article on cosmology in August of this year. It's on Archive. And, he's the one of the big shots in cosmology and good, deep thinker. He has this wonderful review. And he said, oh, yeah, we've pretty much got it all figured out, but this cosmological constant, it's just a terrible problem. Been with people for 100 years. And the reason is very simple. They don't understand what a potential is. And it turns out the electron in an atom is coupled to the electromagnetic field. Well, what electromagnetic field? Well, to them, the only fields there are is electric and magnetic fields, E and B. And E and B have this thing called the Poynting vector, which is the energy carried by a wave of E and B. So if you have a mode of the vacuum, it has to have some E and B in it. And therefore, it will have an energy that they say, well, it's a quantum mode, so it has to have a 0 point energy. Wrong. Just wrong. It turns out that the field that couples to an atom is known to be the vector potential.
Which is the maximum that it could carry?
No, it's a potential. It's like the electrical potential for a charge. If you have an electrical charge. The charge times the potential gives the potential energy of that charge. And so if you have an electrical circuit, which we all do, you have a thing called ground, which is the zero of potential, and you have a power supply, which has some potential. And the energy in the electrons is the charge on the electron times the potential. There's no energy if there's just potential, and there's no energy if there's just charge. It's the charge times the potential. You can think about it like water. I can put water at any height, like you have a lake up in the mountains and you have the water in the ocean. And it takes energy to take a bucket of water from the ocean and carry it up to the lake. You have increased the potential energy. So the gravitational potential at the level of the lake is proportional to the height. And height, in fact, it's the height times g, the acceleration due to gravity.
And what's interesting about that is in that case, you've basically given the water molecules a reason for which they can move and create a great deal of motion, which has momentum, and you can do work with it. And so
Absolutely.
There must be, this ties into our discussion, which I don't expect us to come to an answer for today, about what charge is, because it seems like, those atoms are wound up in a way that when they're able to make contact, that motion can be injected into the system energetically.
Yeah, and it does so through the electrical potential. So the charge is the thing that you multiply by the potential to get the actual energy. So the vector potential is the same thing with respect to current. Current is the motion of charge, but we can get as deep as you want into it, but let's just do the simple thing. So if you have charges moving in a wire, there's no net charge because there's as many positive atoms as there are negative electrons in the wire, but you can move the electrons. So that's a current in the wire, and that's how we do all of electrical stuff, everything. So the idea of a conductor is the fundamental. Conductor is conceptually a region of constant potential full of electrons that can move.
But this gets to a weirdness because the flow of electrons isn't actually what's causing current, right?
It isn't it.
The flow of the speed at which electrons flow is not equivalent to the speed at which current travels. And so it's not a one-to-one relationship between the flow of electrons and the speed of the front of current, right?
Like they had this, are you aware of the Drude model for a while, which was somewhat popular for explaining this, where like the momentum transfer was like something like a Newton's cradle situation where like you pound on one end of a pipe and it creates an impulse at the other end of the pipe very quickly without actually moving the atoms along the chain.
Oh, yeah. Well, that doesn't have to do. The current is the motion of the electrons, but the signal is a voltage signal. So if you have a wire and you change the potential on one end, that travels at some version of the velocity of light.
Much faster than the individual electrons.
Yeah, it's the electromagnetic potential that's propagating, not the electrons themselves. And that's the thing that moves at the velocity of light. It's a little different if you have a transmission line. It's some fraction of the velocity of light, just depending on how the transmission line is made. But we make a living on sending signals on transmission lines, and it's
it makes sense to me, like just because you're changing the whole system, essentially. Like the system is predicated on the height of that potential, really on like how much energy is available to do work in the system. If you change the voltage, you change the whole system all at once. I mean, not
you change,
not
you
at
change,
once, but
yeah, you change that conductor that has potential, and it doesn't change instantaneously at the far end. It's a transmission line, and it involves the electromagnetic field, if you like. But let me finish the thing. The vector potential is just the thing that you multiply the current by to get the energy in the current. And you can think about it as the scalar potential, the electrical potential is just the potential energy, and the vector potential is the kinetic energy of current. And that at a distance is felt as the vector potential. So instead of E and B, it turns out that the vector potential has all of the information in it. It's a 4-vector because the static part of the 4-vector is the electrical potential, and then the 3 components of the vector are the vector. It's a thing that represents the influence of the current at a distance, just like the electrical potential represents the influence of a charge at a distance. Now, we're not talking about wires and stuff. We're talking about influence in space, radio waves, if you like. So the radio wave that is propagated in space is at a distance that isn't close up, is a vector potential wave. It doesn't have energy of its own. It's just a representation of the degrees of freedom of the current at a distance. So there's no energy in the electromagnetic field. The field is a vector potential, not an E and a B like Maxwell thought. Maxwell thought there was a ether there, and it had gears and wheels in it. No, it's a representation of charges and currents at a distance. And there's no energy in it unless there's a charge there or a current there. So they've got the thing all balled up. I worked the thing out in my little green book. It's a whole new way of getting the laws of electromagnetism directly from the quantum nature of a superconductor, which is the perfect conductor. And then it has a quantum nature. And if you just start with that and you work out step by step, you get something that gives all the same answers that Maxwell stuff does, except in tricky situations where it gets the right answer and Maxwell doesn't. And one of those situations is the superconductor. So anyway, they never went back and looked. Here we have these marvelous experiments where we know what happens with a superconductor and how it couples with the vector potential. And the atom, the electron couples to the vector potential, so we know that's how it's coupled. It didn't have anything to do with E and B. You can get E and B. The E is the time derivative of the vector potential, and B is the curl of the vector potential. You get them if you want them, but they're useless for most things. Once in a while, they're useful, like with a transformer or something like that. It's a very useful concept.
And they might help us come to understand the motion of that shell a bit so that we can untangle this concept of charge eventually. I mean, one thing you mentioned that was really interesting was about Maxwell's ether being kicked to the waste bucket. And it strikes me that maybe you don't need this external ether if you adopt a more integrated view of the atoms being interconnected in some way.
Like, what I'm hearing you say is that you're doing away with the idea of an extant field that is always there and is something that is measurable, and instead you're saying that what happens is that there is the possibility of interaction, and there's no energy until the interaction occurs.
Perfect. The that doesn't mean there can't be uh, uh, if there's a current that's changing here someplace, there's a vector potential from it in all directions. But until there's a charge or a current out there that interacts with it, there's no energy associated with it.
So the question is this. We don't deal with the ether anymore because Michelson-Morley, there's obviously no external ether to the atoms. There's no luminiferous whatever. But the electrons, the surfaces of the atoms do seem to extend indefinitely. Would you agree with that?
What?
The surface of an atom is able to extend,
As described by the wave function.
As described by the wave function, extends to infinity.
Yeah, but
hold on.
Out really quick.
Say it again.
It doesn't propagate.
It's not
it exponentially damps so that it doesn't go very far before it's in the noise.
But this question of communication between atoms, if the atoms are communicating with one another, would it not make sense for them to be communicating through these extended tails of the distribution, which is very, very small to the degree of noise?
Yeah, there's excellent observation. So if you have let's say you have two atoms, and this is an analysis that Bill Goddard got straight for the first time in his thesis. You have two atoms. Let's say you have two hydrogen atoms. Now, those hydrogen atoms, if you're at a distance, let's say you make one of them excited. This one's in the ground state, and this one over here, you have it in a first excited state. Okay, they're coupled by the electromagnetic field, and that goes like 1/r. They can also be coupled by the wave function overlap. That goes e to the minus the distance. So there's a distance where the two things are equal. That's very close. When they're closer than that, they're a molecule. And when they're much further than that, they're two atoms coupled electromagnetically. And that's the big effect. And the exponential is way, way, way down by many orders of magnitude.
Is that a continuous shift? So mathematically speaking, is that a continuous shift? You're saying that if they're close enough, they're a molecule. If they're far enough away, their relation is electromagnetic. Is there a discrete break where you can see mathematically that you... And so that's the question. Like, as you pull them apart, you can imagine like taffy almost, right? You have them smushed into a molecule, and then you pull them apart, and there's these thin strings that remain between them.
Yeah.
Is that...
That was Bill Goddard's thesis. And it's so fascinating that it had not been worked out before then. And yes, there's a place where they're about equal. And then when you get further out, you don't have to go very far before the wave function overlap is negligible. But when you get to that point, now you have a three-body problem in the physics view. And the reason is they write a wave function for the two electrons and the electromagnetic field. Okay. And so then you've got the whole thing. And exactly how you do that is tricky, and that's what Bill figured out.
It makes me think of near field and far field interactions as well.
Exactly. Very good.
Okay.
Very good. The near field and far field refer to the same kind of crossover, but not with the wave function, but with the static electrical interaction, plus and minus charges, and minus charges repel and all of that, and the dynamic interaction that happens when they're far enough away that the electrical thing goes like 1 over r squared, and the propagation goes like 1 over r. So it's then the vector potential ends up with what you're left with. But when you're in so it's the same kind of crossover, except it's between the static electric potential and the vector potential.
This makes me think of like the actual shell of the atom being the static potential, the motion of that shell, but then these little taffy portions, as they're pulled out, you're getting into the radiation zone where there's something else going on.
Yeah, and so you just think about how fast each of these interactions. So you got the wave functions, the closest in, it dies out exponentially. Then the electrical, the plus minus charge thing, is what you call the near field of the electrical interaction. And then that dies down like 1 over r squared or so, depending on the situation. And then now you get further away, and now you have the vector potential, which is the thing that depends on the thing changing with time. And so, because there's no current in an atom, in most atoms, some atoms have a fixed current in one of the orbitals, and that's a side trip. So we're talking about the main track here. And you have to be careful to get the orders of magnitude straight, because there's no point thinking about all of the things being big when the big effect is 7 orders of magnitude bigger than the small effect. So then you solve for the big effect, and then you take that solution and see what the next effect, how big the next effect would be compared with that, and just estimate that. And if it's 7 orders of magnitude down, you don't worry about it. And so that's kind of how we engineers. Yeah. I'm going to take a quick break. I'll be right back.
Of course. So it seems like the innovation is that there is a need for an atom to be present or something or charge in order for there to be a current or for there to be some kind of energy between. Like, it's not like there's energy in the vacuum outside of an atom or outside of a charge.
Well, how could there be, though? I mean, it makes sense. Like, if you try to actually give energy a material science definition, it can't mean anything other than something moving.
Yeah, and so I wonder if there isn't if we don't have the ability to ask him about like how it is that it came to be believed that there is something in the middle of empty space, and how that ties to the Nobel stuff, because I think that's important, because the Nobel stuff is about this quantum entanglement, and the quantum entanglement is about this instantaneous information transfer across vast distances. And as far as I can tell, their ability for there to be energy in between atoms that are not in communication is what all of that is based on.
Right.
And there's also the question of like, how do you create an entangled pair to begin with? So we were talking, and one of the questions that I have is how this relates to Clauser's work. To John Clauser's work and the recent Nobel Prize.
Okay, so the details, as I said, are in the last section of that paper with John Clauser.
Yeah, we'll put a link to it We'll put a link to it in the description. And as you said, it's a pretty mathematical paper, but you both did a fantastic job of writing the text in such a way where someone who can't follow the math can still follow the text, which I think
That was the intent. And thank you for saying that, because I put a lot of energy into trying to have description that didn't depend on, you have to have the math because otherwise a physicist can't relate to it. But and you have to show it's right, and so you have to derive all that stuff, and it's not so simple, but it's straightforward once you get onto the track. But yes, so a way to think about it is an electromagnetic connection. If you think about just this the simple, let's do the simple photon first, okay? Because all of the thinking is there. And if you don't get that one, you're not going to get the 3-particle one, which has an atom and 2 receptacles, 2 receiving. See, that the Clauser experiment has an atom that has a 2-step decay in it. So they would say it puts out 2 photons in terms of its transition. And one goes to one atom reception in one atom, and the other goes to another atom in the other detector, and that's what you detect. So let's do the photon, which is just one atom with one other atom, okay? Because and I know this is, you've read this, but let me just do it anyway, okay? Because we've got to be on the same page.
Yeah, explain it for the folks who haven't had a chance to read it yet.
Yeah. So the way an atom works is it has discrete energy levels. And the reason they're discrete is because you solve Schrodinger's equation. It's a wave equation for the electron. The electron's a wave, and the electron can make standing waves around the positive nucleus. And it can make, the simplest one is it just has one maximum, and it's just a ball that dies out exponentially from the center. And then the next one is one that has 2. It's like a hourglass.
The p orbital.
Yeah, and so it has a phase which is different on the top than on the bottom, and it's a stationary state also. Stationary state, the charge isn't moving with time. But if you mix the two just a little bit, and in an atom, it can have some of its wave function in one state and some of it in the other, and the two have to add up to one electron. But the electron can be part in one state, part in the other, and when it does, its charge oscillates back and forth between the two. And in that case, it oscillates back and forth between in the direction that the hourglass is, and it does that at a frequency which is the difference in the frequency of the two levels. And that's just a simple result of the Schrodinger equation. And all it's saying is that the electron is a wave, and that the square of its amplitude is a charge density. That's all it's saying. And when you do that, then and Schrodinger was a guy that figured out that he has a way of writing an equation that gives the result that you observe, because that's what we observe the atoms doing. And de Broglie was the one that saw that the electron had to be a wave, and Einstein liked that idea a lot. And Schrodinger was the one that I forget what scientist it was that when people started talking about the wave, and he said, if there's a wave, there must be a wave equation. What is your wave equation? The very thick German accent. I forget who it was. It might have been von Laue, but it was one of those guys at a meeting, and wonderful. So, and you know the story is Schrodinger went off and figured it out up in the mountains. But
I wish I could go back in time and interject. If there's a wave, something has to be waving.
Yeah. And you know, people get hung up on that because the waves that they know are always waves in something. Like a sound wave is a wave in the air, and a water wave is a wave on a surface of a pond, and a guitar string has a wave when you pluck it, and that's on the. So there has to be something waving. Well, the electron is waving, and its being is its own medium. It doesn't need something to wave in. It's its own medium.
It's waving in the medium of the electron. Like, I think that's fair.
Or like maybe just once we have like a definition for what charge really is, then we'll understand that there's just a change in the surface motion.
Yeah, because this is a little bit of a left field statement, but if you have a material conception of the atom where there is some kind of a substance that the atom is made of, and the electron is the surface of that substance, then if you have a wave in the substance, then there's no ambiguity. It's like the atom itself is resonating, and the stuff of the atom is what it is. And if you look into the nucleus, then the nucleus could just be a different part of the standing wave, and you can have this kind of resonant conception of an object down there that is self-encompassing, where you don't need to have a different medium. It just is the medium. It is what it is.
Very good. You got it. And the proton is a different stuff. It's much denser, and it has its own wave description. It's a different stuff. We don't know what that stuff is, except we know a lot about it, and that's at
least a step in the right direction. I mean, as long as you know a lot about it, you can probably go back and figure out what the stuff is. But I don't want to get too lost in this sidetrack, because I think that what's really valuable right here is that we're walking through the way that your interpretation of collective electrodynamics plays with Clauser's experiment.
Yeah.
And I don't want to get too lost in the philosophy, because we'll lose the thread of that.
Yeah. And it's I try to point out where the edge is of what we know. And there's no point trying to solve the stuff we don't know in 1 hour, because it's
it's one of our favorites. Forgive me, because my entire background, like my PhD, is hard materials science, and it's resonant material science too. Like I worked with the atomic force microscope, and everything to me. I studied actually water's resonant behavior in different confinement structures and so forth. And so it's hard for me to ever not think about things in terms of, especially when I think about things that are resonating. It's very difficult. So you must forgive me, but I'm always trying to come down to what these materials could actually be doing. And I don't expect us to come to an answer. I just can't stop playing with it. So
yeah. Well, I have a material view of the electron. It's a wave, and it's its own stuff. So it doesn't depend on being in something to have its own wave, and it can spread out and have a longer wavelength, and it can be cooped up, and its energy goes up, and so all of that is intuitive. You don't have to go far from where you've been to get that picture. But you have to admit there's this stuff that the electron wave is made of, and I call it the electron. To me, that's
That works. That works fine. Yeah.
yeah. Uh, uh, so anyway, we got that. Now let's just take that picture and say, suppose now I have another charge someplace and I wiggle it. How does that interact with an electron in an atom? And that's the thing that Schrodinger figured out, that it's coupled with the vector potential from the electromagnetic wave. And what's that? Well, there's a deeper question there about how does it get from here to there, and is it in something? But let's just take the observed fact that it has a delay getting there, but it's a wave of the vector potential, and it doesn't have energy until it interacts with something. So it's really a placeholder for the influence of a current here at a distance. Well, when you write down the expression for the propagation of the wave, it's very interesting that it has a solution for a wave that propagates forward in time and the wave that propagates backward in time. And if you superimpose the two of them, you get a standing wave.
This sounds very Feynman. Feynman, how do you say it? Sorry.
Feynman, yeah. Well, Dick, yeah, he was a colleague of mine. Unfortunately, he's not with us anymore, but wonderful, wonderful guy. And he and Wheeler, when he was a grad student, did some work where they did that forward and backward in time stuff. People before them had tried something. They did it the way they did it. It didn't quite get them there, and so they gave up on it. And on the other hand, it stayed with Feynman's diagrams that he's famous for, that people use for fundamental particles and stuff. So it's there in that thinking, but in an odd way. So I won't go there because it will get lost. But Gilbert Lewis had the clearest view of the thing. It, absolutely marvelous, and he actually worked through, but he didn't get all the way there either. I get a little further, not all the way, in the little green book, and then that's a little further still in the thing with John Kramer.
Do you think it had sorry, I don't want to totally derail you, but like with Gilbert Lewis, was it in some part because he was a chemist and he was outside of the hard physics community, or?
Yeah, he was a very independent thinker, even in chemistry. I mean, he came up with the covalent bond, which is all of life is made with covalent bonds. And diamond, silicon, all of those materials are made with covalent bonds. And he invented the covalent bond. So he had to have some wave picture of how that all could work. And so you could kind of think that the two electrons, if they got in phase just right, they could peacefully coexist. But if they didn't get in phase right, they might repel each other. So how would you figure that out? Well, he never did figure it out. It took Heisenberg to figure it out. But he had the idea. And so you can imagine, what that was back then, because this was in 1926, that quote I gave you. I mean, it's when all of this was happening. And he had a a deeper insight, physical insight. And Heisenberg went off on the math route, and that ended up taking over because they couldn't understand physically what was going on. We still don't. But the fact that the math works the way it does gives us a lot of hints about what's going on physically, but it doesn't really get us there yet. But that's the thing for the next generation to figure out.
Yeah.
And the physicists won't
kids.
get it because they won't let the next generation do anything different than just grind on their statistics. But anyway, let's just do the photon because this is really important. So, only thing I have in the entire universe is 2 atoms, and I have one that's in the first excited state, and the other one that's in the ground state. And they're far enough apart that the only thing that matters is the vector potential between the two. There's not enough wave function overlap or static electricity. That's way down in the noise. And so what I have is the dynamic coupling due to the propagation of the vector potential. Okay, so this excited atom, let's say it has a little ground state in it, so then it starts to oscillate. And that's the source of a vector potential which propagates. And now that starts to interact with the other atom. And the way it can interact is it starts mixing the excited state with the ground state, because that's the only thing at that frequency. Okay, well, you say, what's wrong with that? It just propagates out there, and the the vector potential just puts energy into that state, and that energy comes out of this state, and so it makes a transition. All the energy from here goes over there. Yeah, that's half the story. But this atom here, the only way it can lose energy is if there's a vector potential that interacts with it to take energy away. Well, the only way, it turns out, the only vector potential that can do that, if you only have the other atom, is the advanced potential that happens when this one starts the process. So that's before it got to. So it's just exactly what Gilbert Lewis said. He must have had this in his mind when he wrote what he wrote. And so that thing it looks like a standing wave, but it has the vector potential at the source atom from the receiver that sucks energy out, and vector potential from the source at the receiver that builds it up. And they're both exactly equal and opposite in time and opposite in sign. So they do the right thing. And if you just write it down, that's what it does.
So,
and there's no other way to conserve energy.
So if you say opposite in time, do you see something like they're moving away from the 2 different atoms relative to one another?
If you
like a handshake that happens from both atoms in opposite directions?
Yeah. There's many ways you can imagine it in your head. John Kramer has a way he talks about the offer wave and the acceptance wave, and that's his way of thinking about it. But we both agree that it's not 2 separate things. it's happening all as part of the same transaction.
Mm-hmm.
And if you're at one place, you see a perfectly sensible thing. And if you're at this atom, it all happens there. And if you're at this atom, it all happens there. And they're coupled over space-time. So that's another way of saying it. So if you're a special relativity person, that sounds familiar. You're coupled on the light cone. You know how they talk about that. And so that's the way I talk to relativity people. It's coupled on the light cone, so that makes them local on the light cone. Okay. You can also think about what's happening in between. Does the energy flow in between? And we're working on that right now to see if there's a way that can work. I don't know yet, but I think so.
Quite simply, it sounds like the atoms are connected to one another. It sounds like the atoms are connected to one another.
Yeah, they are. They're coupled on the light cone. So that's one way of looking at it. That things on the light cone are coupled, and they're bidirectionally coupled. So Wheeler and Feynman got a little ways there because they're saying, well, when I have an antenna here and I drive it, I'm putting energy into the antenna has to be going somewhere. Well, if you you can say, well, it goes into the wave and use the Poynting vector. But then if you're going to put energy in the field, then you got the cosmological constant problem. So I think of it as the energy being, coupled over space-time. It's a tough one to visualize.
Well, if you have a connection that's static and it isn't moving, then it wouldn't have energy is motion. Is that would you agree with that definition?
Material in motion.
Material in motion.
If it's static.
Well, if it's static, there's no energy because there's no material in motion. If we define energy as
there's only one atom.
Well, or even before there is, let's say that there's two atoms, but they haven't begun this exchange yet.
Okay.
So there's a connection. It's static. There's no material in motion. Therefore, there's no energy that's measurable or no energy that's present there. But once the exchange begins and the material comes to be in motion, then you have something that is detectable, which wasn't there before.
Exactly. That's beautiful. And that's the way I think about it. It becomes a coupling, and it just is, and it manifests at both atoms. And if I don't force myself to put something in between, it's perfectly natural. If I force myself to put something in between, I'm going to have to invent something. And it may be possible. It's like, it's like any of these things. People have always wanted a channel for the energy to flow in, and we could probably do that. But it doesn't work with the Maxwell type thing. It just doesn't work.
Because
and that's
there's no energy there by default.
Well, if we're okay now with the photon, now let's do the Clauser experiment.
Okay.
The Clauser experiment has an atom in, it has an excited state, which is an S state. That's the, you know about S states. They're symmetric in all directions. And the ground state it's going to is an S state. So it has no preferred direction. But it's a two-step transition. So the middle state that it goes through has a wave function like the hourglass. So when you have the excitation start to happen and the wave function of this electron now starts getting some from the center, the charge starts to move. And that charge then couples at the frequency between the top things. And it will be coupled to some other atom someplace. But suppose that atom's in one of Clauser's detectors. It's arranged to make that more likely than it would normally be because he got lenses and all kinds of stuff to make it work that way. So, okay, it's coupled to one of those detectors. Well, now that this atom is moving and the energy comes down, the only way the energy can come down is if you mix in some of the wave function of the bottom state, because otherwise the energy has to stay up here. So now if the energy is starting to come down, I'm going to have the bottom state mixed in. Well, that's a different frequency. So the thing in the middle will be oscillating back and forth with two frequencies. Well, that's okay. But it's one electron. So it's got an orientation all built in because of the first transition. So it's wiggling back and forth here. And that wiggle is in a direction. Okay, what direction will it be in? Well, the direction it'll be in is the direction which will allow it to talk to this other atom. Because otherwise it's got no vector potential over at the other atom. And the other atom doesn't have any vector potential here. So it's remember, a bidirectional connection now. So those two atoms will line up and start oscillating together at the first frequency. So now there's a direction in this atom. Well, it's also oscillating at the other frequency. So it's the same electron in the same atom state mixture. So it's got a direction. And so that direction will be inherited by the other frequency. And so the two polarizations will line up because they share the source atom wave function. The source electron, the very, very same electron, wiggling on that direction. And the only way, of course, that it can know is if it's coupled in. Technically, if you just had a photon that just went with no reverse coupling, you might say it could just fly off, and it would fly off in opposite directions, and it would go through the two polarizers like that. That was the loophole in the Clauser experiment. Is maybe it was just did that, and so of course there was a correlation because of that. So then Aspect went and did the one where he changed the polarizer while the photon was in flight, which of course doesn't mean what you might think, but okay. And so then that couldn't be that you did it with just photons flying away, because then this one couldn't affect what that one was going to be.
I want to take a step back, and I want to outline the design of the experiment for the listeners. Like, we have to assume that they haven't read the paper and that they've heard of the Bell inequality and they've heard of Clauser, and they kind of know what the experimental setup is. But in order to really understand the impact of what it is that you're saying, I think that we have to talk about what the experiment is set up to measure and the conclusions made from that in order to then talk about how a different interpretation is possible.
Right. So we talked about there's an atom that has a two-step transition, and how the electron state in the middle is shared by the two electromagnetic couplings at the two different frequencies. We talked about that.
Mm.
So what Clauser observed was he took polarizers in the two directions. He had a setup where he could focus one of them in one direction and one in the other direction, so that if something happened in the middle, there would be highly likely that one would go off and to the left and the other one would go off to the right. And so then he put polarizers that he could adjust. And on the other side of the polarizers, he put two detectors, one for the frequency of the top one and the other one for the frequency of the bottom transition. So the picture is now we have an atom in the middle. It makes a transition, which is the center energy level is such that it's wiggling back and forth in a direction, wiggling at two frequencies that share a direction because it's the same wave function. And that oscillation is electromagnetically coupled through a polarizer to a detector of one frequency on the right and a detector of the other frequency on the left. Now, the standard picture of electromagnetism at the time was, oh, well, that's just two independent things. There's no reason for them to be sharing any properties because they're independent things. And when Clauser made the measurement, he was expecting to see no correlation between the polarization of one photon and the polarization of the other photon. And by photon, we mean a click in the detectors of both detectors at the same time.
Which says that the signal has gone through the polarizers, and so he has set the angle of the polarizer correctly relative to the emission for there to be a signal at the detectors that are on the outside of those polarizers.
Right. And of course, the way polarizers work, if you get them in the right polarization, you get some transmission. It's never perfect. And if you get them in the wrong polarization, you get zero transmission, which is never quite zero. But Clauser worked very, very hard to get the zero close to zero and the 100% close to 100%. That was the biggest thing he did, because otherwise you could make an argument that it was random. And that's what the Bell inequality is, just a fancy way of saying, how can you rule out it just being random, doing it by random chance? So what he found was there was an extremely strong correlation between the polarization of the two And it didn't depend on the absolute angle. Like if you had the two lined up, you could turn both of them anywhere and you'd get maximum coincidences of the two counters. And if you put them 90 degrees to each other, no matter what the absolute angle was, you'd get almost nothing in both in terms of coincidences of the two. So that's telling you that it isn't that the setup has some magic angle that it wants. It has to do with the atom itself, because that's the only thing that is common between the two. And so the standard way of thinking in the day was, oh, well, they're just photons, and this one goes off to the right, and that one goes off to the left, and they're different frequencies, so they have nothing to do with each other. So they shouldn't be correlated. And Clauser found this very, very large, unmistakable correlation.
And where your innovation seems to come in is that you're like, they're not independently generated events.
Yes. Perfect.
Which is basically just the spookiness comes from the assumption as to what a photon is and where it's coming from. Can you really truly generate two photons that are separate but quote unquote entangled, or are you making one event that goes off in different directions, which because it has this shared core of incidence is related to itself because it's just one event?
And that's an excellent way of expressing it. That it ends up, it's one event, because otherwise it can't complete. So if you think of it as a transaction, that atom can't match the phase with this detector and match the phase with that detector unless they're both right. And so and then what was shown later was that it isn't like you knew ahead of time, so you were going to cheat and let it know, so they could change the thing as the photon process was going on.
Then this is Aspect's experiment. So let's talk about his experimental design and how it changed versus Clauser's. Did Aspect also win a Nobel Prize, or it was just Clauser?
Yeah. It's Clauser, Aspect, and Zeilinger.
Got it.
And it represents the second, third, and fourth observation of this effect at different levels of certainty.
Got it.
Ruling out various random ways of having it happen. There was one observation before Clauser of the same experiment by a fellow by the name of Kocher, Kocher, and the statistics weren't good enough to rule out the thing being some kind of random thing, and but it was a first observation of the effect, and but it wasn't followed up until Clauser followed it up. So, and that's
Go ahead.
it strikes me as some very primitive assumption that was made with the invention of the word atom that might be a crisis at this point, because the word atom essentially means a solitary unit. And it seems to me like this experiment demonstrates that atoms aren't so separate from one another.
Well, what the way they express it is that it can't be explained by something local, and then they go on and on about how they describe that. But as you can see, the intent has been to rule out anything that was just local, and lots of work, lots of arguments, lots of there's been a huge literature on that, which is much more complicated than but conceptually you can see that what axis this connection has to be correlated with what axis this connection is in order for the transaction to complete. And so remember when we were talking about the photon and how the connection between the two atoms builds up as the energy level, the two levels get mixed in each atom. And so during that process, which the statistical quantum mechanics rules out and says you cannot discuss because it's just a probability. You can't talk about how it works. But in fact, that is the period when this transition that they claim is unitary. I think they say it means instantaneous. It means you can't ask about it or you'll flunk the exam. It's that process of when the transaction is happening, when the two atoms are entangled. The two atom that let me be more precise. It's in that process of the transaction when the wave functions of the electrons in the two atoms are entangled.
Where you're basically, it sounds like basically what you're saying is that as the atom that is the emitter is starting to go in between energy levels, it is able to sense the other atoms that are there, and it finds an atom with a corresponding resonance that it is able to make a handshake with, and it is the atoms that are outside of it that it's going to be handshaking with that are defining the frequency that it takes during the transition.
Well, the frequency is dependent upon its two energy levels, and that has to match the atom. So it's not that the other atom defines it, it's that they have to agree.
Yeah, it's like the only connection will happen when there's another atom on the other side that is in some sort of complementary resonance that it's able to talk to.
Exactly. And that resonance has a frequency. It has a phase, which has to line up with the phase of this atom. And it has a polarization.
So, okay, question. If you were to take a different atom, would that change the angle of relative polarization between the two filters in order to generate the same coincidence level?
That's good observation. The polarizer, it isn't a binary thing. So the fraction of the vector potential that gets through the polarizer goes like the sine of the angle between the polarizer's maximum transmission and the polarization of the vector potential. So it's not like it shuts off. It goes down like the sine. So what ended up being the killer was that when the two polarizers were aligned, then you got a maximum of coincidences between the two atoms. And when they were anti-aligned, you got a minimum. And that didn't depend on any absolute. So that was the big finding.
Mm-hmm.
And but it wasn't like all or nothing, because it had to go smoothly from a maximum down to a minimum, and it was a cosine squared thing, and because it was a intensity, not a vector potential. So so anyway, that was the big finding, that the two were correlated, and no simple local model that you could gin up would give you that.
What was Clauser's interpretation of this? I tried to watch some interviews with him, but I couldn't quite grok what he was making of this experiment exactly.
Well, he was the first one to actually bear down on what is it really telling, and his interpretation, which he gave at the meeting where he talked about this, was that it ruled out any kind of local electrodynamic coupling, that there had to be something non-local between the atoms in order for this to happen.
Can we really quickly translate local in this sense? Like, what does it mean for there to not be a local connection between the atoms? It's that there's nothing in between them, and yet they're still behaving similarly?
What they were distinguishing was that there had been Bohm had proposed that, well, maybe there's some special connection that's that we haven't written down, and it's they called it hidden variables, and there was a huge, in my mind, that's the variables aren't hidden. It's a wave function and the vector potential, and they're not hidden at all. They have and that's all you need. But
they were thinking maybe there was like the photon little particle things that were flying off knew what they were going to do before they left, or something like that.
Somehow they had some knowledge of something else. And I've never gotten into the hidden variables thing, because to me it doesn't make any sense.
It didn't work out anyways, from what I understand. They weren't
they were able to rule that out. But it's a long and very complicated argument, because people have different models how it works. And now the way it works in standard quantum mechanics that I described, this n-dimensional space thing, the reason it gives the right answer is that there are three-dimensional spaces. There's one three-dimensional space for the counter on the left. There's one three-dimensional space for the counter on the right. And there's one for the atom in the middle. And then there are two more. There's one for the electromagnetic field between the atom in the middle and the left one. And there's one for the electromagnetic field from the atom to the right-hand one. So when you write all that out, it's chicken tracks in their standard notation. But the electromagnetic field is in common between the two because it has the position of the atom in the middle and the position of the atom it's coupled to. That makes it non-local because it's stating that electromagnetic mode is coupling those two. Well, you just stated that the electromagnetic field was coupling the other two as well. That makes it non-local. So it just turned out, because of the way statistical quantum mechanics is, the way they're formulated, that they use standing waves as the basis set for their electromagnetic modes. And the standing wave has the non-local behavior because it's an extended thing. And in this case, it goes all the way from one atom to the other, one counter to the other counter, because it's in common with. So it's a non-local thing by the way it's constructed in statistical quantum mechanics.
And it seems to relate to the idea of the electrostatic being very contained by the bulk of the radial distribution function, and then like far out you have something else which must be considered non-local, which is outside of that regime.
Yeah, that's the vector potential, which goes out. So just the way the statistical quantum mechanics does electromagnetism, it uses a coordinate system for it. And when it couples to two things that are in different places, that makes the mode non-local.
Mm-hmm.
And so it's inherently non-local. They don't tell you this. They just say quantum mechanics gives the right answer. Well, why does it give the right answer? Well, because the way it's constructed is inherently not local.
And does this help us understand why there's unaskable questions? You mentioned that there's questions you just don't ask, if you want to get the right answer on the test. Well,
the little analysis in the paper I did with John Kramer addresses a question that you are forbidden to ask in the statistical quantum mechanics, because all you can do is construct a Hamiltonian, and all you can calculate are probabilities, and what happens in between is called a measurement. And what it means is something like a click in the counter, and they have their own way of saying what that is. It's that atom getting into its final eigenstate. Well, a photon, every time a photon happens, the two atoms go into their final eigenstates. So they're making measurement every time there's a photon. Has nothing to do with measurement. Has to do with a transaction getting to a final state, not being hung in the middle someplace. And when it's hung in the middle with another atom, it's entangled. They don't tell you that either. So what's happening in the Clauser experiment is, while the transition is happening, the atom in the middle, the wave function of the electron in the source atom is wiggling at two frequencies. They're correlated in direction because the wave function is set up in that direction because of the nature of the state. And it's coupled to the two other atoms, and until they agree and each of the other atoms can absorb the energy, it doesn't complete. And when it completes, then that's what they call a measurement. And in this case, it's a very good name for it because it's a counter that it went into. The process would be no different if it went to something besides a counter and wasn't counted. It would still be doing the same thing. And then would that be a measurement? Well,
I mean, if you made a secondary detector that could detect the event, then you could take a measurement of it, right? It's just like if you put something in the way and what you're doing is a measurement, but it's still happening, you could probably make something else that could sense the event even in the absence of the direct measurement.
Yeah. The reason they talk like that is that so the only thing they can calculate. And so they have to call it a measurement because their idea is that the only thing you can calculate is you prepare the state in some mixture of eigenstates. Then you let it go, and then you take a measurement. That's the only thing you can do in statistical quantum mechanics. And then the measurement will give a statistical outcome. And since that's all you can calculate, they believe that's all nature can do.
Before we finish though, I want to get to the bottom of what aspect did differently.
Oh, what aspect did is he said, well, maybe somehow the fact that these polarizers were all set up, they've been set up for a long time because you had to crank them around and everything, and then they're sitting there just waiting. And because they're just sitting there, maybe somehow that information of where they are gets encoded somehow in something. And so it's like kind of predetermined because they've been set up that way a long time, much longer than it takes light to get anywhere. So what he did is he set up so that that he could tell when he excited the thing in the middle. And then he waited until it was the photon from that would be like halfway between. And then he changed the polarization of one and saw how it was related to or he changed both. So it wasn't sitting there so that someone could have known ahead of time and affected the measurement. So and they have very fancy ways of it's called a loophole, and they have several different loopholes that are ways that you can fool a thing into being correlated when it really isn't down deep in the physics. And they're very clever ways that they think about it, and I don't think about it that way, but it's fine.
So is it fair to redefine this photon as an event that the reason that it's quantized is because this entire transaction needs to occur for the photon to be a finalized event?
Yeah, of course, they don't agree. They don't admit that there's a transaction.
Right.
They think of everything as it's a probabilistic outcome of this big matrix thing they have.
Mm-hmm. Mm-hmm.
So to them, it's a discrete event. It can't have any structure, because if it did, and they don't know it, then they'd have to admit that something they don't know, and they want you to believe they know everything.
Mm.
So it's just the hubris of the statistical quantum crowd that's in the way of thinking about. John Kramer in 1980 realized from the Clauser thing and the things that even before Aspect had done it, he realized that there had to be this bidirectional connection, and he's championed that for all these years. And the physicist mantra: if we can't find an argument that shuts this guy down, we have to agree to ignore him. So that's been the nature of the reception to John's stuff.
When did this really gnarly confrontational physics attitude, did this start with Einstein and Bohr? Like, when did physicists start punching each other in the face?
It was the Heisenberg-Bohr crowd and the Schrödinger-Einstein thing kind of got polarized because Einstein kept saying, yeah, that's fine, but something's happening with that interaction, and we need to be able to understand it. And they said, no, there's nothing more to understand. There's nothing but statistics, which is the dumbest thing you could imagine.
It just seems so unscientific.
There's always more to understand.
Yeah.
And
it seems like just like shutting down conversations is, it's becoming more and more of a problem in our civilization today. Yeah. And it seems like one of the deepest threats that we have facing us overall as a global society. It's like people trying to ask questions and being told that they can't talk about that. It just seems so dangerous.
Well, it's the antithesis of what science is about.
Totally.
Any result in science always opens more questions. John Wheeler had the best picture. He said, we live on an island of knowledge in a sea of ignorance. And as we expand our island, the perimeter of the edge of knowledge gets bigger, not smaller. So this idea of the end of physics is just completely nuts. But
it's a terrible disservice too to the next generation of potential scientists, And I'm always trying to find new ways in my own lectures, like at the university, of inspiring the students to see that there's so much work left to be done, without, of course, giving them the unsettled feeling that we know nothing at the same time, because it's this continual process of updating our understanding. And sometimes we do have to make big changes, but there's certainly a lot that we do know every time we figure out something we don't know, because that's actually knowledge by itself.
Yep. And it's very important that starting in the very beginning, we open to our students the notion of what we don't know, what the edge of knowledge is, because we always have partial knowledge, and the students need to know where that edge is, because that's the place they'll find good stuff to discover. And there's more of it all the time, not less. And so it's Wheeler's picture is just beautiful.
Do you think I'm kind of like beating a dead horse here, because this is something that I love to talk about, but it seems like you don't need to be concerning yourself with the edges of what's known if your job in the workplace is going to be to take the knowledge that's accumulated and apply it to, creating new engineering systems.
Which is why you have to separate out science and engineering, because if you're learning to be a pharma student or a doctor or somebody who makes airplanes, you don't occupy yourself with the question of, do we understand what a molecule is? Because that's not the path that you're on. And I think that we've done a huge disservice by taking the sciences and by folding them under this umbrella of applied knowledge exclusively, almost. Like there's some basic research, but it's kind of the redheaded stepchild of the entire organization. And so there's not a lot of prominence to it, and the ideas that come out of it are often summarily dismissed because engineers are like, well, we already have something that works. Statistical mechanics is perfect for what we want to do. Why are you making this more complicated?
Yeah. They, my own experience, living on the edge between science and engineering is that at any given point, you have a pretty good idea if you're doing science or if you're doing engineering. But a lot of times, as an engineer, you'll be wanting to achieve something, and you'll realize that there's some science to be done before I understand what to do. And so you have to go off and do some science to figure it out. And so I've spent my life going backwards and forward across that. And then when you get a scientific result, you say, oh, that could be useful. And so you think about that. And so the point is, of course, you're right that once you have the basic knowledge and you go to make a gadget with it, then there's a lot of hard work just making the gadget work and getting it going. But you don't know when you set off on, like, Charlie Talon's going to make a laser, right? Well, that's a fundamental science thing, but it's also a great gadget. We wouldn't have our modern world without them. So, that is more what I've seen than the sharp distinction. And of course, it's become more and more that the applied people had to work out the science because the statistical quantum stuff just wasn't cutting it. And so yeah, it's usually clear when you get up in the morning if you're doing science or engineering, but I go back and forth all the time, and that's more what I see as actually happening, and the new phenomena are almost always discovered as experiments, not some theoretical brouhaha. So it's yeah. You got to be careful, and it's just amazing now the new physics. There's this idea that have been propagated. In fact, physicists teach their students now that the electromagnetic field is quantized in little packets of h bar omega energy. Well, the people doing frequency combs, Ted Hench and the guys in NIST in Colorado, they're getting the waveforms at optical frequencies and tuning up the waveform so it makes the transaction go just right. Nothing quantized about the electromagnetic field. It's the transaction that quantizes because of the discrete levels of the atom. That's what makes it quantized. And in fact, von Laue had a big argument with Einstein about his quantum being a property of the radiation field. He said, no, you haven't shown that. You've shown that the interaction is quantized. And Planck said the same thing. He said that you can't take the radiation field to be quantized. You have not shown that. What you've shown is that the interaction is quantized.
And so looking into the future and the state of the field right now, what do you think has to happen in order to shift the understanding from this spookiness to something that actually has a material basis?
Well, the old saying, science progresses one funeral at a time. Having them stuck in the mud, old, crotchety know-it-alls get out of the way is a big thing. The other thing that's happening is people like Sabine Hassenfelder, who have these wonderful, she has these wonderful programs which debunk a lot of the know-it-all stuff. And it's a huge service to have somebody tell it like it is, because people were afraid to say anything because they lose their job. And by the way, Scientific American has a really good article about this Nobel Prize for this year, and it spells out how these guys were told, if you're going to work on this, you won't have a job.
Wow.
Here was fundamental physics. They were, and nobody would hire them, and their advisor said, no, you can't work on that. You'll be unemployable. So physics is a discipline. Theoretical physics is a discipline that if you ask fundamental questions, you won't get a job in theoretical physics.
Which might mean that change has to come from outside of that discipline to some extent.
Absolutely. Well, where it's come from is the applied physics, quantum chemistry, quantum optics. The quantum optics stuff, a huge amount of good quantum stuff has come out of there. And you just ignore and if the statistical thing helps, well, it almost never does, because it doesn't allow you to talk about the interaction of, the conduction band and the valence band of a semiconductor at the energy to make a traveling wave in a semiconductor laser. The statistics aren't what you're about there. And it's all about waves matching up wavelengths and that. So we all had to go off and invent it our own way, thinking about it, and going along pretty well. It's just that the notions still get in the way, because the notion that the radiation field is quantized is deeply engrossed in the physics where they're teaching, as the beginning introduction, they're teaching that rubbish. And so then nobody would go off and do one of these wonderful frequency comb thing, because of course you couldn't do that if it was quantized. But still so there, it's going to take young people, largely in the applied sector, where they're finding these really nice effects, and then let's hope the thing gradually gets to be okay to talk about.
Mm-hmm. I think it's going to be amazing. I mean, I honestly, we don't really have the scope to go into it now, but it maybe gives us a little bit of insight into gravitation as well, if we start thinking about atoms as connected to one another. And I think that it's a real game changer. I was so excited to find your work, and like I said, these are ideas we've been kicking around for a while, and just to see, I mean, you formalized it. This book it's not a new book, right? This is an idea you've been working on for a very long time.
Well, not as long as John. Okay. John started in 1980. I started in 1990 some odd, on the little green book.
It was actually one of our listeners that brought us. I said it was actually one of our listeners that brought you to us, and so I just wanted to put that on the table, which is like, the people who listened to the show found your work and they loved it enough to be like, you have to talk to this guy, because he has a vision of the world.
Well, tell them hello. It's great to meet both of you. And yeah, sometime we can talk more about gravitation, but it's a longer story and much less immediate. The electromagnetic stuff is absolutely immediate. I mean, we have a Nobel Prize, and no one in the discussion of the Nobel Prize said that it was about electromagnetism. Zero. And that's what it's about, is electromagnetism. And the only person that saw that was Ed Janes. And I don't know I think I have his quote here. Yeah, here. Let me get that out of the way.
When was this?
This is Ed Janes.
Is this a recent remark?
No, Ed Janes, 1972. This was at the meeting where Clauser gave his talk.
Check, got it.
And Ed says, what it seems to boil down to is this: perfectly harmless looking experimental fact, which amounts to determining a single experimental point with a statistical measurement of unimpressive statistical accuracy, at a single stroke can throw out a whole infinite class of electromagnetic theories of electrodynamics, namely all local causal theories. This will surely go down as one of the most incredible intellectual achievements in the history of science.
Whoa.
So no one, except I forced this into our, Clauser's a Caltech alumnus, so they had a big story about it. I had to force them to put that in. Nobody even knew about it. It's about theories of electrodynamics. And the reason Janes knew that is he had been cooking up other ways of treating quantum systems, and Clauser had shown they didn't work. In fact, the next sentence that Ed Janes said, and my work will lie in ruins. So he was saying that this was so important that a lot of what he had done was shown to be wrong.
Wow, that's so honorable.
Yeah, that takes a huge
And he's
amount
so
of
honorable. This surely go down to one of the most incredible intellectual achievements in the history of science. He knew that because he'd been fighting to make it work. And here's this thing that showed that it can't. Well, he was working with old-fashioned Maxwell stuff, and that doesn't work. So, and he didn't get that far. Unfortunately, he's not with us anymore. A wonderful man. But, yeah, so you see how stuck the thing is.
Yeah.
That nobody even knows there's questions there that have been deeply dug into.
Well, I really appreciate you coming by. That's sort of the entire purpose of our project, is to uncover those unknowns and really check out what's going on at the edge, before we make these grand theories. What's happening in the foam in between.
Yeah, this is great. Really good to talk with you again.
It's fantastic.
And we'll stay in touch. Good luck with everything.
Thank you so much, Dr. Mead. It's been a real pleasure.
Okay, take care.